Hey all, welcome back. It's Professor Marinos again. And over the last few lectures, we have explored the thermodynamic basis for why equilibria exist in chemical systems. Now in this lecture, we're going to shift gears a little bit and go to actually working out some equilibria. So in a chemical system, given a starting state of certain concentrations of products and reactants and a temperature that that system's at, can we predict the equilibrium state of that system given a known set of chemical reactions that can occur in that system? Well, the answer is yes, and I'm going to show you how. I'm just going to work a bunch of example problems for you of increasing complexity so that you can really get familiar with how these equations work. And then in future lessons, you yourself will practice these until you can do them like the back of your hand. So let's get started. For this lesson, the learning objectives are for you to be able to, by the end of this video, solve equilibrium problems of increasing complexity and also solve a system of equilibrium equations. So a system in which multiple reactions can occur that are all governed by a common reactant. So the product of reactant A might feed into the reactants of reaction B. And how do we solve systems where multiple chemical reactions can occur? So let's launch right into this. I'm just going to solve some problems for you live and uncensored.
Now you need to make sure before you watch this video that you know how to make an ice table. So I will refer you to this link provided here, which is also provided in your course materials, as well as a crash course chemistry video that also covers this subject, which will also be provided in your course materials. So make sure you watch those videos and understand the concept of an ice table before you make any further progress in this video.
Okay, so we'll start off with a relatively straightforward example to begin of using giving K value to calculate equilibrium concentrations of a reaction given a known amount of initial concentrations. And we're going to explore this through the Haber-Bosch process, which is the process that is used to manufacture nitrogen fertilizer all across the world. All nitrogen fertilizer starts with the Haber-Bosch process. And this process is the reaction of one atom or one molecule of dinitrogen gas combining with 3 molecules of dihydrogen gas to produce 2 molecules of ammonia gas with the equilibrium constant K shown here at 375 degrees. So if we start off with each of these reactants, nitrogen and hydrogen, at partial pressures of 10 bars each, we put them into a reactor at 375 degrees Celsius, what is the partial pressure of ammonia gas that is produced at equilibrium? Okay, let's begin by writing our equilibrium quotient Q. And again, this equilibrium quotient is for the reaction N2 gas plus 3H2 gas yields 2NH3 in gas. So our equilibrium quotient will be the activity of the products, which is NH3 in a gas, and because it's a gas, the activity is equal to its partial pressure, raised to the stoichiometric coefficient, so 2, over the partial pressures of these two raised to their stoichiometric coefficients, is to 1, and the partial pressure of hydrogen gas raised to the 3rd. Okay, now let's make out our ice table. For this reaction, we need all 3 of these to be in our ice table. So let's start with the initial concentration of nitrogen. We know that this is 10 bars, so just fill in 10 here. And for hydrogen, we also know that it's 10 bars. So put 10 and 10 there. And it didn't say that we started off with any ammonia in the system, so I think it's safe to assume that that is 0. Now, as this reaction progresses, what is the change in concentration? Well, for every amount of nitrogen consumed, dinitrogen gas, which we can call X, some amount of nitrogen gas, we consume 3 times that amount, or 3x of hydrogen gas, and we produce 2x of ammonia gas. Now the change is going to be negative because these are being consumed, and this is going to be positive because that's being produced. So what is the expression for our equilibrium in terms of x? Well, it's the initial plus the change. So for dinitrogen, it's going to be 10 minus x. For hydrogen, it's going to be 10 minus 3x. And for ammonia, it's going to be 0 plus 2x, or just 2x. Okay, so now that we have this ice table filled out, we can plug this in to our reaction quotient and set it equal to K. K again is 8.1 times 10 to the negative 6. So just set the reaction quotient equal to K, plug in these expressions for x, and then solve for x. So we get 8.1 times 10 to the negative 6 equals 2x, the product, right here, squared, over the expression for the equilibrium pressure of nitrogen, multiplied by the expression for the equilibrium pressure of hydrogen, cubed. Because remember, you have a coefficient 3 there. And let me just solve this real quick for you in my head. What are these numbers? You have negative 125. You have negative 0.153. You have 0.133. And you have 145. All of these are solutions for x. But not all of these are solutions for x that have a realistic physical interpretation. So as you know, you can't have negative concentrations or negative pressures of a gas. So what you need to do is you need to take all these x's, which are possible solutions for this equation here, and figure out which of these give you a positive partial pressure at equilibrium for all of your gases. If any of these terms come out negative, then you know that that is not a physically possible solution. So for 2x, you know x must be positive to make this positive, so we can already just cross off all of the solutions that are negative. And then 10 minus x excludes this one, because 10 minus 145 is also a negative number. So you're left with the value of x that makes sense as 0.133. Now, simply plug this x into the expression for the equilibrium concentration of ammonia, which is 2x, because that's what we're ultimately trying to solve for, the partial pressure of ammonia gas at equilibrium. Equals 2x equals 0.266 bar. So there's the solution. Given our initial starting conditions, we can expect the reaction to produce at equilibrium 0.266 bars of ammonia. So great job, Richard. Okay, you were probably just thinking to yourself, wow, Richard must be a mathematical genius. He just pulled those 4 values of x right out of his head, seemingly from nothing. How did he do that? And the answer is I cheated. I used a website, Wolfram Alpha. Wolfram Alpha is like the Google of math. So just go to wolframalpha.com to solve any sort of complex rational or polynomial equation that you really don't want to solve out by hand. I don't begrudge you this at all. This is not a math class. This is a chemistry class. So please let a computer do some hard math work for you so that you can focus on understanding the chemistry. So just go to wolframalpha.com. You can just click right here and type in any old equation that you want. So our equation was 8.1 times 10 to the negative 6 equals 2x squared divided by 10 minus, I actually should put in 2 parentheses there, 10 minus x times 10 minus 3x cubed. Close out that parentheses and just hit enter. And there's some little gnomes that work overtime and solve this for you. And so the first thing you want to do when this comes up is you want to check to make sure that Wolfram Alpha interpreted your input correctly. So you could have misplaced a parentheses up here like I was just about to do, or you could cause any number of different errors, and Wolfram Alpha will think that you want it to solve an equation that you don't indeed want it to solve. So just make sure that this matches what you want to have solved. And then once you verify that, you can just scroll down and voila, Here are some nice answers for this very difficult rational equation, just out in the open, ready for you to use in your chemistry. So that's how I did that. Feel free to make use of Wolfram Alpha when you're solving problems in this class. I think it's a better use of your time than solving this by Newton's method by hand. You'd be here for a month. Okay, now let's add a little wrinkle. Now we're not going to be given K, we're just going to be given the Gibbs free energy of reaction, so we have to determine K, and then use K to solve for the concentrations of products and reactants in reaction. And the problem is as such. A rare rainstorm in White Sands, New Mexico soaks the gypsum sand dunes. These are beautiful white gypsum sand dunes, dissolving the gypsum in the following reaction. Gypsum calcium sulfate times 2 waters yields calcium in solution plus sulfate in solution plus 2 H2Os with a standard Gibbs free energy reaction of 24.07 kilojoules per mole. Now, the rainwater falling on these dunes isn't pure distilled water. It has a little bit of sulfate in it because it's slightly acidic. It's acid rain coming out of Los Angeles. And so at 25 degrees Celsius, what is the equilibrium concentration of calcium in the water of the dunes? Okay, so begin by recalling that the Gibbs free energy of reaction is equal to the standard Gibbs free energy of reaction plus RT log Q, or log your reaction quotient, and that the Gibbs free energy of reaction at equilibrium equals 0. And at equilibrium, we will call QK. So this is our equilibrium constant, the reaction quotient that sets this equation equal to 0. So you can just rearrange this to be, we did this in the last lecture. This is natural log here. And we can just take the exponent, or raise everything to e on both sides, or raise e to everything on both sides to arrive at k. So we have e to the negative. So we can just plug in the values that we know. We know the temperature it occurs at, we know the gas constant, we know the standard Gibbs free energy reaction, and we can determine K. So this is going to be e to the negative 24.07, the standard Gibbs free energy reaction, over ideal gas constant. And again, I match the units between these two numbers, multiplied by the temperature that the reaction is taking place at, 298.15 Kelvin. Of course, this always has to be Kelvin. And this equals K. And let me just solve this in my head real quick. Okay, it is 6.06 times 10 to the negative 5 for this reaction. Okay, now let's use this K value to solve for the concentrations that we want to solve for. Okay, let's start by writing our reaction quotient for this chemical reaction, which is the products. So the first product is calcium, raised to their stoichiometric coefficients. One calcium ion was produced per 1 molecule of gypsum dissolved. And again, these are just concentrations because we can just assume for most dilute solutions that concentration is equal to activity, multiplied by the concentration of sulfate, raised to its stoichiometric coefficient, 1. And then there are also 2 waters produced, so we need to have the activity of water raised to the square. But of course, the activity of water is 1. Activity of any solutes or solvents are 1. Any liquids, so we just cancel that out. We don't have to worry about water. Over the activity of gypsum, raised to its stoichiometric coefficient 1, but again, the activity of any pure crystalline solid is also 1, so this cancels out too. We don't need either of these in the reaction quotient. So our reaction quotient is just the concentration of calcium in solution multiplied by the concentration of sulfate in solution. Okay, so now let's build out an ice table for this. We have calcium 2 plus, we have sulfate 2 minus. So what was the initial concentration of calcium in the water? Well, this rainwater coming into the system didn't contain any calcium, or at least the problem didn't say that it did, so we could just assume that that is 0. But we said that there was some sulfate that came in with the water, and it was acid rain, and the concentration of that was 5 millimolar, or 0.005 molar. So fill that in. Okay, and now this water dissolved gypsum in the sand dunes. And for every molecule of gypsum that it dissolved, it produced one atom or one ion of calcium and one ion of sulfate. So we can just say that the change is X for both of these. And so what is the equilibrium concentration of both calcium and sulfate after the change occurs that brings it into equilibrium? Well, it's just initial plus change. And so 0 plus X is X. And sulfate is going to be 0.005 plus X. Okay, now we can just set our reaction quotient equal to K. K again for this reaction was 6.06 times 10 to the negative 5. So 6.06 times 10 to the negative 5 equals, put the expression for calcium in, X, put the expression for sulfate in, 0.005 plus X. And now you can just solve this. You can use Wolfram alpha if you care to. This is also just easily solvable by the quadratic formula. If you just move this over and FOIL this together, you end up with x squared plus 0.005x minus 6.06 times 10 to the negative 5th. So you can just plug this into your quadratic formula, and that would be x equals 0.005 plus or minus, or sorry, negative 0.005, negative b plus or minus the square root of b squared minus 4 times a, 1, times c, which is 6.06 times 10 to the negative 5, all over 2 times a, which again is 1. So you can figure this out. You'll end up with two solutions. One solution will be negative, or one solution will make one of these terms negative, and one solution will make these terms both positive. And the one that makes them both positive is x equals 0.006 approximately. So just take this x. We are asking what the equilibrium solution of calcium in the reaction was, and that is simply just x. So at equilibrium, the concentration of calcium equals 0.006 molar, or 6 millimolar. So, problem solved. Okay, so I just want to take a little detour real quick and explore the Gibbs free energy reaction, the standard Gibbs free energy reaction, and a useful quantity that you can derive from this. So you'll recall again that the standard free energy of reaction for any reaction is the enthalpy of the products multiplied by their stoichiometric coefficients, the enthalpy of formation, all summed up, minus the enthalpy of formation of the reactants multiplied by their stoichiometric coefficients, all summed up, plus the sum of the entropy of their products multiplied by the temperature multiplied by the stoichiometric coefficients, minus the entropy of the reactants multiplied by the temperature multiplied by their stoichiometric coefficients. Wow, that is such a mouthful, but you can just see it written here on the screen. And because this is such a mouthful, and because this involves so many terms, you can also define something that's pretty useful by rearranging this, just by taking out all the sums and grouping everything by participants in the reaction. And so you can define something which we call the Gibbs free energy of formation for any participant in a reaction, which is simply the standard enthalpy of formation for this participant in the reaction, either a product or a reactant, minus the temperature times the change in entropy that is caused by going from elemental form to the form of the participant in the reaction. And so this is a useful quantity to have for any participant in a reaction, the standard free energy of formation for a reactant or a product, because then you can also just rewrite the equation above, the Gibbs free energy of reaction, the standard free energy reaction, as just the sum of all the Gibbs free energies of the products multiplied by their stoichiometric coefficients minus the sum of all the Gibbs free energy of formations of reactants multiplied by their stoichiometric coefficients. So oftentimes you'll see tabular values for selected chemical participants in reactions that are just given as the standard Gibbs free energy of formation. And this is how you can calculate the standard Gibbs free energy of reaction from those. Okay, let's use these Gibbs standard free energies of formation to actually solve a problem. So first we're going to calculate K given the standard free energies of formation and then solve for concentration. So what we're trying to solve is this problem that groundwater with very high levels of zinc, so an undetermined but very high concentration of zinc in it, percolates into an alkaline lake with a constant carbonate concentration of 0.5 millimolars and a temperature of 25 degrees Celsius. This mixture of this zinc-rich water with carbonate-rich water results in the precipitation of smithsonite by the following reaction. Zinc 2 plus carbonate 2 minus yields zinc carbonate in solid form. And I've given below the Gibbs free energy of formation for all the reaction participants. So the EPA sets a limit of 5 milligrams per liter zinc for drinking water as a safety limit. Given that a lot of the zinc precipitates out via the reaction above, is it safe to drink this water that's in this lake? Let's find out. So the first step to solving this problem will be to determine the standard Gibbs free energy of reaction through the formula that we just looked at for the Gibbs free energy of formation for all the products and reactants. So to do that, we'll sum all of the stoichiometric coefficients of the products multiplied by their Gibbs free energy of formations. So the one product that we had was zinc carbonate. The stoichiometric coefficient in the equation was 1. And the standard Gibbs free energy of formation was negative 731.6 kilojoules per mole. Everything is going to be in kilojoules per mole. Now, so this takes care of the products. Now let's subtract the same for the reactants. So we had one reactant, zinc 2 plus. Its stoichiometric coefficient was 1. And its Gibbs free energy of formation was negative 147. And we have another one to subtract, minus carbonate. Its stoichiometric coefficient was 1 again, and its Gibbs free energy of formation was negative 527.9. Okay, just do this math up, and you arrive at a Gibbs standard free energy of reaction of negative 56.7 kilojoules per mole. Okay, now that we have this standard free energy of reaction, let's find out what our equilibrium constant is, K. So again, we'll plug this into the formula that the negative standard free energy of reaction, so negative D Gibbs free energy of reaction, which is 56.7, equals RT ln K. And R, is 0.008314.5. I hope you can rattle that off by now. The temperature of the reaction is 298.15 Kelvin. We said 25 degrees Celsius. Everything always has to be in Kelvin. Times log K. So now just rearrange this and exponentiate both sides. We have E to the 56.7 divide these through, cancel these out, 0.008314 times 298.15, and this equals K. And I'll just calculate that. It is 8.58 times 10 to the 9th. Okay, so now that we have our equilibrium constant figured out, let's figure out what the concentrations are in our system. Okay, so again, recall our reaction was zinc 2 plus carbonate 2 minus yields zinc carbonate as a solid. Okay, so let's start off by writing our reaction quotient. We always want to do that first. And the quotient is the activity of the products. Zinc carbonate is a solid, so I won't even bother writing it out this time. We just note that that is 1, and that's the only product that is in this reaction, over the stoichiometric coefficients of the reactants multiplied by their activities, or, the activities of the reactants raised to their stoichiometric coefficients. So that's Cn2 plus raised to 1 multiplied by carbonate 2 minus raised to the 1. Okay, so now let's fill out a rice table for this. Or an ice table, whatever you want to call it. Okay, so the question stated that there is a constant concentration of carbonate in the lake. We don't have to worry about calculating anything for this because this has an activity of 1, so this doesn't factor into this reaction quotient at all. But for carbonate, we know that this is 0.005 at the beginning of the reaction, or sorry, 0.0005, or 5 millimolar. And this remains constant throughout the reaction, so the change will be 0 because there's no change in carbonate as this reaction proceeds. Now, how is this possible? This is possible because the amount of carbonate in the lake might be so great that the small input of zinc doesn't change that, and carbonate is also in equilibrium with the atmosphere. We're going to learn a lot more about that. But just know that it is possible that even though carbonate is being consumed in this reaction, there'll be carbonate added to the system due to other equilibria that will cause the total change in carbonate to be 0. So I don't want to get too big into the mechanisms here, but just know that since the problem said that the carbonate concentration in the lake is constant, we can just write the change here to be 0. And so at equilibrium, the carbonate concentration will still be 0.0005. Now let's look at zinc. We don't know the exact amount of zinc coming in or the concentration of zinc coming into the water. We only know that the water is very, very rich in zinc. So let's just say that the initial concentration of zinc in the water was X, an unknown quantity X. And the change, similarly, we don't know because we don't know how much we started with. We don't know how much we can remove via this precipitation reaction happening here. So we're going to make that an unknown too. We'll call it negative y. And so at equilibrium, we have the initial plus a change is x minus y. Now, this expression is kind of hairy because we have two variables. But what's key to recognize here is that we weren't asking to calculate the initial concentration or the change in concentration. All we want to know is the equilibrium concentration. And so because we're not having to solve for either of these variables, we can simply just define a new variable, z, equals x minus y, and just solve for z in this reaction quotient. So, you know, this is kind of one of the reasons why I don't particularly love ice tables, is that sometimes you end up doing a little bit of extra work filling in these values when actually all you need to do is solve for a value that doesn't relate to the initial concentrations or the change in concentrations, depending on the problem. But I still think that this is a useful framework to overall understand how reactions are progressing towards equilibrium. So now that we have this this expression for the equilibrium concentrations, the concentration of zinc equals Z, the concentration of carbonate equals 0.0005, we can plug this into our reaction quotient, setting Q equal to K. So we have 8.58 times 10 to the 9th equals 1
over the expression for zinc, which is Z, times the expression for carbonate, which is constant again, 0.0005. So now you can just rearrange this. I would just first put all these to the -1 to get the Z in the numerator, and then divide through by 0.0005, and so you end up with 1 over 8.58 times 10 to the 9th multiplied by 0.0005 equals Z. Okay, so now we have an expression for Z. Let's just do this on a calculator any way that you can solve it. It ends up being 2.33 times 10 to the -7. And now the equation, or the question, was asking for the concentration of zinc 2 plus at equilibrium. You can see the expression for equilibrium of zinc in terms of Z is simply just Z. So the zinc concentration equals 2.33 times 10 to the -7 molar. Now, what we wanted to determine was, is this amount greater or less than 5 milligrams per liter, which is the drinking water standard? So to do this, we just need to multiply through by the molar mass of zinc, which is 65.38 grams per mole. This is moles per liter. So the moles cancel, and you're left with grams per liter. And this equals 0.00015 grams per liter. Or that's 0.015 milligrams per liter. That's not approximate, that's exact. And this number here is much less than the 5 milligrams per liter drinking standard. So we can say that this water is safe to drink. It gets my Richard Marinos check mark of approval. Okay, let's solve another problem where we're given a K and we're asked to calculate equilibrium concentrations. So wastewater from a potash plant, which is a K2SO4 fertilizer, potassium sulfate fertilizer, is evaporated in a retention pond outside the facility to recover the dissolved potash that's contained in the wastewater. So you have potash that's going in to this water, it's dissolving, and then they evaporate off the water to recover that potash. And as evaporation proceeds, the potash precipitates out of solution so that the water in the retention pond reaches equilibrium with respect to the concentrations of potassium and sulfate, according to the following reaction. 2 potassium ions in solution plus a sulfate ion in solution yields a precipitate of K2SO4, potassium sulfate. And the equilibrium constant of this reaction, K, is 0.56. So at equilibrium, what is the concentration of sulfate in the wastewater? So as this pond dries out, what is the equilibrium concentration that the water in the pond gets to before it completely dries out? Let's solve this. Okay, so let's begin by writing out our reaction quotient. So the products, activity of the product is potassium sulfate in solid, and so the activity of a solid is 1. Again, we can just easily set that aside. And then you'll recall that the reaction is K2SO4 is produced by 2K plus SO4 2 minus. Okay, so the denominator of the reaction quotient is going to be the activity of potassium, K plus, raised to its stoichiometric coefficient, so square it, multiplied by the concentration of sulfate, raised to its stoichiometric coefficient, which is 1. Okay, so now let's make an ice table for this. Again, we can ignore doing anything with potassium sulfate because we don't need to calculate any expression for that because we already know the activity of it. It's 1. Okay, so this brine that was produced from this factory, this salty water, was produced by dissolving potassium sulfate.
And so while the problem doesn't state the initial concentrations of potassium and sulfate that are in this water, we know that it must occur in a ratio of 2 to 1. 2 parts potassium to 1 part sulfate, because potassium sulfate is 2 parts potassium to 1 part sulfate. So we can write the initial concentrations as unknown, but we know that potassium is going to be twice the concentration of sulfate. Okay, now as the water evaporates, we don't know how much potassium is precipitated out of solution because we don't know the starting concentrations. It wasn't given to us. But again, we know that for any change in sulfate, we have to have twice the change in potassium. So again, we can just write this, the change, as negative 2y, and the change in sulfate as negative y. And so at equilibrium, you have 2x minus 2y, the initial plus the concentration, or plus the change. And for sulfate, you have x minus y. Or you can rewrite this as 2 times x minus y. And this is just x minus y. And so just like in the last problem, because we're not being asked to compute any of these values or any of these values, we can just disregard the fact that we have 2 variables that we don't know the solution for, and we can just redefine both of these as z. So if we can get one variable in the equilibrium concentration expressions, we know that potassium will be 2z and sulfate will be z. So now we can just plug this into our reaction quotient, setting it equal to k. 0.56 equals 1 over the expression for potassium, 2z, squared, times the expression for sulfate, z. Or, in other words, 0.56 equals 1 over 4x cubed, or 4z cubed, I'm sorry. Okay, now we can just solve this. I would flip it around. 1 over 0.56 equals 4x cubed. This is going to be 1, sorry, I keep writing x, I mean z. That's 1.8 equals 4z cubed. Or 0.45 equals z cubed. The cube root of 0.45 equals z, and that equals 0.77. Okay, so now we have an expression for z, and the question asked, what is the equilibrium concentration of sulfate in the system? So now just take the z value, plug it into the equilibrium expression that you have for sulfate, which is, again, just z. It won't always work out this way, but it did work out this way in this situation. And you have the equilibrium concentration for sulfate equals 0.77 molar. Now, if I had asked you to calculate the equilibrium concentration of potassium, you would just plug in this z to this expression 2z, and you would arrive at concentration of potassium in equilibrium is equal to 1.54 molar. That's about the level of math that I can handle doing on the fly. Okay, so up until now we've been considering reactions where there's only one reaction occurring in a system. But now let's look at what happens if you have multiple reactions occurring in a system, and where the reactants of one reaction can be the products of another reaction. So let's get back to the dunes of white sands, New Mexico, one of the most beautiful places in the world. Some of these dunes contain appreciable amounts of anglesite, which is lead sulfate, PbSO4, that can also be dissolved in rainwater. Assuming this time that the rainwater is pure, so there's no sulfate coming in with the rainwater, just to simplify things, and that the following reactions can take place. Lead sulfate dissolves to form lead ions and sulfate ions. Calcium sulfate gypsum dissolves to form calcium and sulfate ions in water, with the following equilibrium constants shown here. Please calculate the equilibrium concentration of lead in the groundwater to begin with, assuming that both of these reactions can take place. And then what would the equilibrium concentration be of lead if the dunes were only anglesite, if there was no gypsum involved in the dunes? So let's work that. Okay, let's start off by making 2 different ice charts.
one for the lead reaction. And one for the gypsum reaction. Okay, so the water coming into the dunes we said was distilled water. So the initial concentration is 0 for all reactions. And we don't exactly know how much lead sulfate has been dissolved yet. So let's just call it X. But we know that it happens in a ratio of 1 to 1. Lead sulfate dissolves into 1 part lead and 1 part sulfate ions. And so the equilibrium concentration will be X and X for the amount of sulfate dissolved from lead sulfate and the amount of lead dissolved from lead sulfate. Now let's go over to the calcium sulfate question. Similarly, we don't know how much of this will be dissolved, but we know that for every part calcium dissolved, we also have a part sulfate dissolved. And so the equilibrium concentrations of calcium and sulfate, considering just that one reaction, will again just be Y. And so the expression for the equilibrium concentration of lead is X. The equilibrium expression for the concentration of calcium at equilibrium is Y. But both of these had sulfates dissolving out of them. So equilibrium for concentration for sulfate is X plus Y, because you have both reactions contributing sulfate to the ultimate reaction. Okay, so now let's take this to our equilibrium constants that were stated in the problem. The lead equilibrium constant, K, is 3.9 times 10 to the negative 8th. And we know that this equals concentration of lead times the concentration of sulfate. Or to rephrase this, we have X times X plus Y. And the equilibrium expression for the dissolution of gypsum was 6.1 times 10 to the negative 5th. We know this is calcium and sulfate. Or to say this another way, Y times X plus Y. Okay, so now we have two unknowns and we have two equations. This is solvable. We have no more variables to solve for than we have equations to solve. So let's work on solving that. So just to restate the equations that we already know, we have 3.9 times 10 to the negative 8th equals X times X plus Y. And we have 6.1 times 10 to the negative 5th equals Y times X plus Y. Okay, so now all we need to do is isolate one of these variables in one of these equations and then plug it into the other equation and solve for that variable. So you'll recall that the concentration of lead is X, and so that's the one that we want to solve for. So we'd eventually like to isolate X by itself in an equation. So let's start by solving for Y down here and take it from there. To solve for Y, we will what the heck? Okay, let's solve this equation for Y to begin with. We have 3.9 times 10 to the negative 8th divided by X minus X equals y. So I just first divided through by this x, and then I subtracted an x from both sides. Okay, now we can use this value for y and plug it into our second equation down here for these two y's. So we'll get 6.1 times 10 to the negative fifth equals 3.9 times 10 to the negative eighth over x minus x multiplied by x plus 3.9 times 10 to the negative eighth over x minus x. So these cancel. And so you now have if I just multiply this term through onto this term, the x's cancel here, and this x becomes, or this becomes an x squared on the bottom, and you square the top two. And this all equals 6.1 times 10 to the negative 5. Okay, so now it's just a question of rearranging it to solve for x. So we can do that next. Let's pick back up solving this. We have 6.1 times 10 to the negative 5 equals 3.9 times 10 to the negative 8 squared over x squared. Then we can just subtract this right here, and this makes this quantity not that, but 6.10039 times 10 to the negative 5. And it's kind of silly to subtract that because, you know, these numbers didn't start off that accurate to begin with. But just for the sake of completeness, we can go ahead and do this for this exercise. If you're in a real world situation, though, you might just say, like, oh, this number is negligible compared to this number. So I'm just going to say it's 6.1 times 10 to the negative 5. Anyway, continuing on solving this, let's take the inverse of both sides to bring the x to the top. So we end up with 1 over 6.10039 times 10 to the negative 5 equals x squared over 3.9 times 10 to the negative 8th squared. Bring that over to the top, and you end up with, if you just take the square root of this whole thing, which I think we can go ahead and do now, x equals the square root of 3.9 times 10 to the negative 8th squared over 6.10039 times 10 to the negative 5th. Plug this in your calculator, and what do you come up with? You come up with x equals 4.993 times 10 to the negative 6. Okay, so now we have solved for an x. That is great news. Now let's just get back to the original formulas that we developed. This system of equations here. Where does x fit into this? X is the concentration of lead. That's exactly what we wanted to solve for to begin with. So we can finalize our answer. The concentration of lead at equilibrium will equal simply 4.993 times 10 to the negative 6 molar. So, voila. That was a long problem, but we slogged through it. Now I want to consider what is the equilibrium state if you are only dissolving this lead sulfate and there was no gypsum in the system. Let's consider that. So if you only had lead sulfate in your system, the equilibrium constant wouldn't equal x times x plus y. It would just equal x times x. You plug in x for lead, x for sulfate, or x squared. So if x squared equals 3.9 times 10 to the negative 8th, then x, or the concentration of lead, would just be the square root of that number. So
So if there's only lead sulfate in the system and no calcium sulfate in the system, you would have x squared equals your equilibrium constant, 3.9 times 10 to the negative eighth, or x, your lead concentration, would equal 0.000197, or 1.97 times 10 to the negative fifth. So you can see here that because there's gypsum in the system, because you have something else that's dissolving sulfate, you have a pretty substantial increase in the amount of lead, or you have a pretty substantial decrease in the amount of lead that can be dissolved, simply because you also have sulfate contributing to this equilibrium. And this is called the common ion effect. So if you have a salt that's like calcium sulfate, and you're trying to dissolve another salt that shares an ion with that, like lead sulfate, the solubility of that lead in that lead sulfate is going to be much less because the other salt, the calcium sulfate, is contributing sulfate to that equilibrium constant, and you have this x plus y thing going on instead of just being x squared. So this is the common ion effect. The common ion effect reduces the solubility of the counterpart of the shared ion.
So this video is probably giving you some familiarity with the techniques that you'll use to solve thermodynamic problems. But familiarity is not enough for our purposes. We need you to be fluent in thermodynamics. You need to be able to do these equations like the back of your hand. And so what we're going to do is, just in class, you're just going to work a lot of these problems. The only way you get better at doing these is through repetition. So get ready for that.